But I would like us to transition to our next topic, which isn't especially named very great, but that's also kind of the textbook name for it. It's just system hacking. And let me talk about what that means. It's really that next stage. So we've done our footprinting, our reconnaissance. We've done some aspect of the scanning and enumeration. There was one more subtopic at the end of that scanning using the Nmap scripting engine, and I'll try to bring that back into this topic because it is also related. And now it's really, we know what systems are up, we know what hosts are up, we know potentially some information about what services are available, and there is a point to that, right? In some sense, doing the enumeration is its own valid separate task, which is understanding the network configuration of a given organization and the individual hosts and services and operating systems and things like that. But usually the goal, if we go back to our sort of hacking methodology, is, okay, we've understood this information. We know that there's a web server at this IP, and it's running this particular set of web services on this web server. And what can we do next with that information? How can we potentially use existing vulnerability and exploit databases to determine what things can be actually taken advantage of, what additional access we can potentially get from the current sort of publicly available accesses here. This does tend to be, well, it's got a couple aspects of it that we have to kind of keep in mind. First off, it does tend to be very operating system dependent. To some extent, that's becoming less and less true over time. But we do tend to look at, and in the lab you see that as well, things one can do in attacking a Windows system or gaining access to a Linux system tend to be fairly different for historical reasons. Also, for this class, and it's partially due to kind of the expected technical prerequisites for this class, we focus entirely on using existing vulnerability and exploits versus attempting to craft our own. There are other classes that do focus more on things like reverse engineering of software and hardware to better understand how to craft your own exploits. That tends to be at that 4,000 to 5,000 level here at Iowa State, because you really do. And it's one thing to read an existing exploit or vulnerability. It's something quite different to create your own. You really do need fairly low level, what I would just call computer engineering knowledge to be able to craft those things yourself. You have to understand software construction at a level that sometimes just takes some time and maturity, that it just an introductory course doesn't necessarily give you. Oftentimes for these exploits, you have to have what we would call sort of architectural or micro-architectural knowledge, the kind of thing that you can learn. And one doesn't have to be a computer engineering major to learn those things, but it's just something that maybe takes a little bit more time in your career. And having said that, there's a lot that can be done when looking at just existing exploits versus attempting to craft your own. There's also kind of a resource constraints issue there, that maybe this class we could work together, and by the end of this semester we could potentially find one new vulnerability and craft one new exploit potentially. If it's truly new, there's some risk there, versus looking at existing ones, we can explore a lot of different ones and see what their impacts are. And otherwise, we're just continuing our steady state schedule with Lab 3, where you're applying some of these concepts in the lab. And today is MQ04. Like I said, we're about a half day behind what we're doing pretty fine here. So we're going to look for our services, what is running on this computer. The assumption is we already know that to some extent. We have the tool's best guesses as to what is running at a particular IP address. The next step is, how do we gain that access? What is potentially insecure about a particular piece of software running on a system, and how can we determine that? How can we find the relevant exploits, and how would we actually apply those existing exploits? Separate but not exactly the same concept, and we'll kind of split that up, is looking specifically at authentication and passwords and some common historical flaws with regards to how we handle passwords and do authentication. It is related, but we're going to start now more about software vulnerabilities and how one can be exploiting them. This is now, if it was somewhat debatable in the prior stage, whether this was a more active or passive stage, when you're port scanning something, does that count as kind of actively attempting to access a resource? And I said, well, it's probably okay. We Nmapped computers on the Iowa State and subnet without much fear of reprisal. So it was kind of an edge case there. Here, it's really no longer an edge case. Now we are we know something about a machine, we want to basically attempt to break into or take down or violate confidentiality, integrity, or um, otherwise just do something kind of potentially malicious to a machine. Again, the difference between someone just hacking to a machine and following this kind of ethical hacking framework is that issue of consent. The tools are still the same. There's not a separate set of white hat versus black hat tools that people use here. The difference is legal and or maybe ethical frameworks that are in place that involve having permission before you start these steps. And you would have some sort of legal agreement as part of a pen testing team that would say, you're going to stop right here. You're going to stop at the point where you discover vulnerabilities. You're not going to actually attempt to exploit those vulnerabilities. Or conversely, what isn't really shown here is it tends to be a feedback loop as well, or at least an iterative process in which you find machines that are publicly available, you potentially gain access, you use that access to leapfrog onto additional machines. So it depends on the particular agreement. There's no one way to do it. But again, that's what differentiates and why what we're doing is fine to kind of teach and for you to learn and apply in the lab versus just applying this to any arbitrary machine that you happen to find as you are scanning machines around you. This issue of, if nothing else, consent, that it's being done with permission of the machines, the owner of the machines that you are scanning and now attempting to actively hack into. There's a little bit of what I would call alphabet soup in this topic, but it's all pretty important stuff. So the only approach I have to that is I'll try to go slowly. What I ask from you is if I say something and it doesn't make any sense, please stop me now versus just kind of shutting off your brain as we kind of go through some of these things. What will otherwise happen is you'll mistakenly believe you understand what I'm talking about, but if we didn't go into the right amount of detail or go slowly enough, you'll have a really kind of surface level knowledge. The truth is, security is a massive field, and there has been long recognized that there needs to be ways to kind of shepherd all the different types of vulnerabilities and corresponding exploits into some sort of common framework so that we have just a common language to describe and compare and explain the different vulnerabilities and weaknesses that are out there. And so when we talk about CVE, and we're going to use that term a lot this semester, and if you're familiar with the term, that's great. I find that people who know what a CVE is, it's actually good to know what it literally is at a lower level, so we're going to do that. That stands for Common Vulnerabilities and Exposures. Maybe knowing the acronym isn't what is important, but what's important is how they actually come about. They are not a magical thing. There's a process associated with them. They are an attempt via a kind of publicly agreed upon, federally funded framework to provide a structure to software and other types of vulnerabilities, a way to describe weaknesses in systems and softwares in such a way that we can have a conversation that removes at least some of the ambiguity in talking about these. So a CVE is a vulnerability or itself a data exposure here. There are going to be multiple different databases of these CVEs. One is the National Vulnerability Database, but what we're going to see is that there's more than one organization that takes responsibility for coming up with these CVEs, and so there are different databases that combine and provide that information to you in different ways. But starting with the concept of CVE and that there is a National Vulnerability Database is a good starting point for it. First off, you can actually learn a lot just by going to any of the CVE databases and just to gain a slightly better feel for what a CVE actually looks like. We do a little bit of that in lab, but we also just tell you, apply this exploit for this particular CVE, which is good kind of proof of concept. It is good experience to do that, but it also allows us to kind of hand wave around our way around of what an actual CVE is. So I just picked two that are somewhat relevant to our course. These are not exploit databases, of which we also provide some examples of. These are the vulnerability databases here. Let me see if I can bring up an example here of what I was talking about. It would be in here somewhere. Okay, so this, for example, is what a CVE entry looks like. I picked 2021. This is a Canvas CVE. There's no shortage of Canvas CVE. So Canvas, literally the learning management system or software, whatever it is that we use for this course. It is a complex piece of software that the university pays a lot of money for. And because it's a complex piece of software with a lot of different use cases, it has software vulnerabilities associated with it. So there is an entity that determines certain things about it. Year discovered or year at least privately disclosed, just sort of an ordered numbering. And then we'll talk a little bit more about this in a few minutes here, but what's called the vector or the score, the CV severity score. And we'll talk about that, what otherwise looks like kind of gobbledygook, but isn't all that complicated. What it means for a CVE to have a particular vulnerability. We have to be a little bit careful when we talk about this, that it's not all that scientific how one acquires a vulnerability score. And what we will also see is it's sometimes a matter of great debate and angst and infighting as to what a particular score should be for a CVE. When we look at the scoring simulator, you'll see it's just a spreadsheet, and it's sometimes somewhat subject to opinion what score and what list of categories a particular CVE would have. Generally, what a CVE database is going to tell you is potentially what software weakness potentially is the cause of this CVE. What was wrong with the process or software development flow or configuration that allowed this vulnerability to exist? I'm going to talk about a few more of those in a little bit here as well. And then also links to potential exploits or proof of concepts for what does this vulnerability mean in practice. I didn't check these. These are going to be legitimate links generally. So this is in Canvas. The claim is that if a student has access, and I did look this up before, to the Canvas API, the ability to do automation in Canvas. If I want to create a new assignment in Canvas, I go to the web interface, and I click 8,000 buttons, and I get my assignment posted to Canvas, and I configure every little detail, and it's frankly quite awful, but that's what we do for our job here. Or there's an API. There's a way as a software developer I can say, create function, make micro quiz for, and it has the right calls to the API, and it would push it to this course. So that's an API. There's an API key. There sometimes can be reasons for which we may want students to also have access to an API for their own course. Some classes may experiment with this where I want students to be able to submit their assignments via a programmatic method, as opposed to you having to go in and upload the PDF and fill in things in a text box. Well, wouldn't it be nice if you could just do that from the command line or from your lab computers without having to pass a bunch of files around and open up a web browser? It turns out, at least when this vulnerability was active, that was not a very good idea, because the developers either didn't think about it or weren't entirely aware that it turns out that at the time, if a student had access, it can access the entire course, including anything that I, as the instructor, left unpublished or left locked for future time. It didn't check any basically authentication-based permissions on a particular course when the student API was active. To me, as the instructor of a course, that's bad. Okay, in a class like this, I guess I would argue, if I did give you Canvas API access and you used it and you brute forced every possible file ID and you grabbed all the quiz questions and, more power too. I guess I'd be very happy if you did that at the end of the day, right? At least for that one particular student who did it, I'd be like, fine, great job, good proof of concept. You can be done with the course. I wouldn't want the whole class to do that, I guess. But that's a pretty big security vulnerability, and that's an example of a CVE for a particular product that we use. We go back to the site here, and we look at the score it received, and there's different versions of the scoring system that says this is only a medium vulnerability. Well, medium is in the eye of the beholder, right? I guess it's not leaking, student personal details. There's maybe no legal repercussions of having that kind of access. As the instructor, that's a pretty big vulnerability. Iowa State, I think, has recognized the vulnerability associated with Canvas API, and they've disabled it across the whole university now, relatively recently. Another example is, and there's all sorts of Discord vulnerabilities that you would be able to find. This one's a little bit more interesting that it's listed as 9.8 critical. And here's two separate links which show that here is someone's proof of concept. And this one's a pretty simple README file. So we use our Discord, some more than others. And the examples are a little confusing what it's actually doing. So it's a tool that's provided in a separate link. And in doing so, it allows some sort of root access to the same machine that it's being run from. I think the implication being that if I'm able to get a user to click on a very particular open Discord link on Mac OS in this case, it would potentially provide some sort of remote shell access to the user's machine. You know, in looking at that one, that proof of concept was a little confusing to me because at least here, it's from local machine to same local machine, and so you already have shell access to get shell access. So that's still potentially a vulnerability to me. That's not a critical vulnerability that a user who has shell access is given another avenue for shell access. And what's interesting is the weakness is perceived to be in the underlying web engine that runs all sorts of applications these days. And this is from the developers of the Electron engine. And I won't go through all of this. Basically, they disagree. They say, hey, this CVE was filed against effectively our software that Discord and other apps are using. And if you were to read that link, and it's available in the slide that we have here, their take is, I don't think this is not critical at all. This is not actually an issue at all. And so that's when I mentioned that you have this attempt to kind of categorize these vulnerabilities. It's not all that scientific. There's a little bit of maybe opinion engineering and also just sort of politics involved as well. I guess it's also just a matter of one's perspective. For me, it seems to me as a user of both Canvas and Discord this semester, assuming both those vulnerabilities were still present and available, the Canvas vulnerability would be a much bigger problem. It would be more critical to me personally than the Discord vulnerability, given the nature of it. I think developers are also kind of naturally defensive about their software, and to the extent that vulnerabilities are serious or not. And we know that's the case. And it's not just the National Vulnerability Database. There are other numbering authorities that allow organizations to kind of assign CVEs for their own products. So it's an interesting space where you have this effectively federal agency, the Metric Corporation, that does their own attempt to provide. Yeah, go ahead, sure.
How indirect does something have to be for it to get assigned or like with skills? Have you heard of like cloud skills?
Sure.
Would that be considered like a vulnerability? You just have someone
So
download a skills file.
So that is a good question, and the actual nature in which someone decides, yes, this is a vulnerability, not a vulnerability. You get a taste of it when you go back to the CVE website. First off, I would love, let's just search. There is a search in here somewhere. Just to answer the specific question of there's going to be a million AI chatbot based skills. I don't know if I want to look for Claude specifically. Let's look it up. Nothing as of yet, but maybe that's not a great search term. Let's just look for cloud in general, or spelled incorrectly. Those are MCP servers. So specific things, I haven't looked at this, so I'm just clicking on a random thing. This is talking about the sandbox not working properly when you tell Claude, please run this code, stay within your home, don't try to access my other files and things like that. There's all sorts of things that it doesn't actually listen to. That was granted a high, but not critical severity here. These things have to be reported. And they don't have to be reported by, in this case, Anthropic themselves. It could be any user of a piece of software who has the ability to report a CVE. Then there has to be a decision-making mechanism by which, in this case, if it's in this database, the Metric Corporation, NVD, says, yes, this is a severity, and here's the score we are going to assign it. But as part of that process, there is some negotiation, some communication with the actual developer to say, here's why we don't think this is an issue, or yes, we agree that this is a CVE, but we don't actually agree that it should be a this high of a severity of a CVE. And so there is that kind of back and forth there. So I think that kind of answers your question that, you yourself, if you think you've discovered something, There are some steps of disclosure one should follow, but you can file a CVE in it. And also, these companies themselves also have the ability to assign CVEs for their own products. There is a little bit of self-dealing when that's the case. So if Microsoft is assigning a CVE for Microsoft Teams, for instance, um, they have some reputational aspects at stake there as well. Are they going to assign as high of a severity as possible? As we look at the CVSS scoring system, I think you'll see it is just a matter of what do we think the vulnerability characteristics are, and then the score is just a spreadsheet or just a formula that gets calculated based on this. Yeah, go ahead.
So can you go back to the CE website real quick?
This one right here, yeah.
Why is NVD golden and then GitHub is only bronze? I've always wondered what the valuation is.
I don't know the color coding of that. In fact, my color sense isn't good enough to even agree with you that that's gold versus bronze here. NVD is considered like the kind of federal approved, federally standardized, organization and database for this. So that is like the prime database for CVEs. GitHub also has the ability to create these things as well as a software developer, but GitHub is also part of Microsoft as well. And in this case, for this particular one, we might have looked, this might be a fairly recent one, right? So this is just this week, right? And that was just because we happened to search it up. In this case, GitHub says it's high. NVD hasn't provided their assessment as of yet. They may agree, they may disagree. The examples I've seen that are X number of years old, they tend to have the same number if there's multiple authorities associated with it. But as you can kind of get a feel for, it isn't this truly kind of scientific, everyone agrees process. It is kind of a human-driven process, something of a political process at the end of the day as well. A lot of alphabet soup here, hence the picture of alphabet soup. Mitra itself certainly looks like it's an acronym. It's something MIT, but it's not. Maybe at one point it was. It's not an acronym. They also manage a couple of other things that we'll talk about later. The common attack pattern, enumeration, and classification, or just CAPAC, and then the attack matrix. We will talk about that in the context of these vulnerabilities. The other acronym I do want you to understand, and we'll talk about them, is this concept of the common weakness evaluation. It is an attempt to provide a more standardized way to think about why the vulnerability exists. CVSS tells us to some extent, as I've already provided a couple caveats, how bad is this vulnerability. CWE, as well as we'll talk about the CAPEC as well, CWE talks about why does that vulnerability exist? What could one, in this case, developer of Claude Code, what could they have done better potentially, or what kind of pitfalls did they trip and fall into that allowed this vulnerability to exist? It's one of those things that tends to only really be determined kind of after the fact. And despite all best efforts, including amazing new programming languages and frameworks and renewed attention to software security, well, the trend is actually a little interesting. We'll talk about that in a second. But despite all that decades now of renewed focus on software security and writing software that doesn't just get you the correct result, but is also more robust to malformed input, unexpected race conditions, exceptions, and things of that nature. It just is a matter of fact that software has also gotten more complex, more internetworked, and vulnerabilities are still a thing. They're really not going away. What has changed, I guess you could say, is the type of vulnerabilities over time that were considered the most important here. So what this is a chart that's attempting to show in the CVE database what broad categories of software weakness, so CWEs, they fall into. There's also a little bit of alphabet soup here. Later, when we talk about web applications, we'll talk about SQL injection and cross-site scripting and XML something or other, XXE. We'll get to all those eventually, in cross-site request forgery and all those sort of things. But you can actually see, and it's sort of color-coded here with a gradient as to what things have become less important, what things have become more important. Cross-site scripting, which we don't need to necessarily understand today, and involves kind of providing verification of input data from one site and subdomain to another was not considered as important, or there weren't nearly as many vulnerabilities. Now, with all sorts of tools that are available to kind of automate the testing for that, we see it kind of grows in terms of its relative count here. Other ones that may be interesting is, we may think that we have all sorts of programming languages today that really prevent memory corruption and overflow type of errors in our memory. Well, maybe not enough people are using them or using them correctly, because it's still very much a real issue today. Input validation, and this is another thing that we'll talk about a little bit later. That's also mostly a web application concern. That seems to be one that potentially enough commonly used web frameworks are now sort of aware of that issue. It's becoming potentially less and less, at least, a discovered number of vulnerabilities. This is raw count. It doesn't speak to the severity of the vulnerabilities. It also just shows that there's been awareness of some of these issues, again, for years and years and years, and it's not a solved problem. It's a good thing for you. There's employment opportunities for you. There's still vulnerabilities for you to find and explore and exploit, but there's a lot of these things here. So the CWE is a separate, kind of more static database of, like I said, things that are wrong with software or system configurations, or potentially hardware security as well. There's over 1,000 common weaknesses that are broken into 3 different main categories. One is more kind of conceptual vulnerabilities. Then we'll talk primarily about software engineering issues, but there are also hardware design vulnerability issues as well, electrical and computer engineering issues, if you want to call it that. Here's an example CWE. So this is what a CWE looks like. It is a description of a flaw in a process, generally. In this case, in a software development process. And the whole point of it is, again, to kind of tie it to a particular vulnerability. So there's a direct connection and correlation here. A piece of software has a vulnerability that potentially can be exploited because it has a common weakness. It has a weakness in the software. It's kind of tautological definition that if there was no weakness, there would be no vulnerability, or you haven't discovered the vulnerability yet. So this is an example of visualization of a common weakness here, common weakness evaluation. These tend to be toy examples. And so I never want you to look at the database of CWEs, and they all provide some sort of example or proof of concept. I think it's easy to look at them if you do have some programming experience and say, well, I would never do that, right? I mean, of course, what a terrible programmer created a use after free error in programming courses, generally system programming courses, low-level programming courses. We talk about memory allocation in course after course after course. And it's something that as you're debugging your own code, you have to be aware of in program after program after program. And so, humans are fallible, right? We make mistakes, and even despite understanding this issue for forever, for almost as long as software development, it's still not really a solved issue. We look at the CWE, and this is no longer like top few, but it's still on that top 10 list of a common software bug that maybe people who should know better are still doing. But again, when you look at the proof of concept that's provided on that website, they try to make it as succinct as possible. So in that sense, yes, you look at this, you say, well, of course I would never do such a thing. But now when we're talking about, and let's talk about this example, a use happens on this file, and 3 hours later in the execution, 74 files over, the free I have that backwards. The free happens in this file. The use happens 60 files over, 2 hours later in the execution of the code. Maybe when that's the case, it's not that obvious that you have a use after free error. This is C code. I've done a show of hands before. How many of you have seen C code before, have some C code? It's not gonna be everybody, because it's not a requirement to be cybersecurity, person that you have real deep kind of C programming knowledge. I also don't want the takeaway to be, well, as long as I don't program in C, I won't have this issue. Any language that does direct management of memory can have these type of errors, use after free errors, and even languages that provide runtimes that really attempt to hide memory management implementation details from you can have these type of errors. They tend to be worse when that happens because they're more infrequent, and they tend not to even be in code that you yourself are really directly responsible for as the programmer. We can walk through this example since I think enough of you have done C. I won't ever ask you to kind of replicate this yourself, but I think enough of us have seen C programming that it shouldn't be totally foreign for us. This is a contrived example. We have a structure that is just including a single integer value inside that structure. We allocate a pointer on the stack for a type of that structure. We then separately allocate a single integer. So that is step one. That is, we have allocated memory. Set it to some value. Doesn't really matter. We've used the pointer. We then free the memory. That's good programming practice, right? We use the memory. We don't need that run calculator integer variable anymore. We have then freed the memory. That is step two here. Then separately, we then allocate this unicorn counter and say, give me a memory allocation. In this case, memory allocation, size of structure. It's a little hard to see. It's going to be the same amount of memory. Allocate, if the integer was 4 bytes in this case, or 8 bytes, whatever your system may need, that allocated 4 bytes and then freed those 4 bytes. This line of code is going to also allocate 4 bytes and then store some value corresponding to those same 4 bytes in memory. And then you have some block of code here where you say, well, if there is anything valid at the pointer, so we reference this pointer again, then I guess execute a shell. It's a toy example. Do anything, I guess. Doing anything on that line would be a use after free error. And I agree. You look at that code, if you were to tell me, well, clearly that's a bug. I ran free, the pointer is no longer valid. I then reference that pointer that's no longer valid. What's going to happen when I run that code? Well, nothing good. That free command is also not magical. It's updating a table that's saying, for all the objects that this program has allocated, here's whether they have memory, how much memory, where the memory pointers are pointing to. Freeing it doesn't like physically remove anything from memory, right? Freeing the memory just kind of updates a table somewhere else that says, yeah, that pointer that was valid is actually no longer pointing to anything valid. Unless there are some other protections in place, it's not randomizing the value. It's not changing the actual value pointed to by pointer. Depends on how the particular memory allocation strategy is going here. But we have what is something that's local here, but allocated. There's the pointers on the stack, but this is allocated on the heap. This is also going to be allocated on the heap. There's no guarantee you have a particular heap allocation algorithm in place, but for many common ones, it's going to want to just reuse the memory that it previously had allocated. Why not, right? I had allocated 4 bytes. Hey, I don't need them anymore. Let me reclaim those 4 bytes. Now the next time I want to allocate 4 bytes, oh, I have 4 bytes right here. I'm going to put it in the same place. What winds up happening is even though you have code that should not execute because you explicitly freed that run calc pointer here, there is actually happening to be something. There is a valid pointer that one can follow. It's not a value of 0. It's a value of 42. It's going to actually execute that shell. Again, you would never write those 5 lines of code like this, but the free of run calc could have been in one function all the way over here, and only in a certain series of edge cases of a whole bunch of nested if-else statements and etc. does that other line of code actually run, and then you wind up with an occasional use after free bug. So that's an example of a common weakness. Someone wrote a piece of code that it won't be in 4 lines. It'll be in 4,000 or 4 million lines of code where allocated memory, freed it, and still use that same pointer. And maybe most of the time, it would just crash software. You attempted to use a pointer that was invalid. That's just a bug. You get a segmentation error or some sort of runtime fault. That probably still qualifies, though, as a CVE for the software, because the general assumption is that if you have that pattern in which someone has access to memory that they shouldn't necessarily have access to, it is possible to have some sort of arbitrary code execution. This is one of those things that becomes a little bit of a debatable topic when the CVE gets created. If I'm just able to crash the software, well, that's not good, right? You know, being able to crash a piece of software in an unattended manner. It's not as bad as being able to remotely create a shell based on the vulnerability in the software. It's oftentimes a matter of degree and sometimes even just pure semantics of, if I can do something like this, how much control, how much of a real vulnerability is that in nature? In general, if you have this, that is a bad thing. This is the 2023 listing of the top 10 CWEs, in which in 2023, use after free was still the number one most commonly found. It's some combination of total number and the severity of each one. I didn't update this slide, but you can go yourself and see the top. Let's see if I can find it here. The top in 2025, the top CWEs, and things have changed a little bit. We don't have to go into all of these. I think it's a little interesting what is now the number one weakness, and it's interesting to me because I don't think there's one obvious answer as to last 2024 it was number 3. Before that it was even lower on the list, and now it's moving up to now the number one weakness that is corresponding to these vulnerabilities. That's improper neutralization of special elements used in an OS command. The numbering does kind of imply at what point was it kind of put in the database. So it is an old vulnerability in that sense. It's not a newfangled technology or a new thing that didn't exist 10 years ago. The idea behind this, and I don't know if the graphics is all that exciting, is that there's a user who is effectively tricked into running a script that seems okay but is actually vulnerable, and then the vulnerability is in some sort of shell scripting or bash scripting or just automation PowerShell scripting that the user is effectively choosing or being tricked to run on their system, that is using things like not necessarily escaping properly or by setting a variable to something that's kind of hidden. It does kind of weird things like delete all files or leak information and things like that. A shell script gone wrong, something that was always possible. I don't have an answer. I haven't seen an article as to why this is now number one CWE when you look at the 2025 database. I have a couple theories. That's all I have. One is, I think this is a kind of vulnerability that's pretty easy to spot. And so tools that can automate the detection of that kind of weakness may be growing in usage and popularity. The other trend, and this is just my old hat being put on here, when I was your age, installing things via command line, run this shell script to install this software to do this was extremely common. That's how we installed software. If it wasn't just a Windows, type approach, that's how we installed. That's how we all interacted with software. We were kind of command line natives and only had to do app managers and program managers as kind of a secondary approach to installing software. But then the trend was very much to get away from that, right? Everything became App Store. Everything became, Windows Store, Microsoft Store, and you would install from kind of trusted, if not first parties, trusted third parties who took the responsibility for kind of gatekeeping what software you were allowed to install. But I'm noticing the exact opposite. The trend is kind of reversing itself now, that the number of pieces of software that I see these days that say, maybe it's cutting edge stuff and not typical user stuff, which is, please run this arbitrary shell script to install the software, is actually growing in popularity nowadays. So that's my guess as to why this has gone from a less important weakness to a much more important weakness, is what was old is now new again, that you want to install this new chatbot or other thing, the command to do it is actually you run curl, you download this arbitrary binary blob off a company or third party's website, and you run it in your own shell, sometimes with super user privileges, to actually install software on your systems. The software is maybe less mature in terms of the installation path than it used to be. And maybe because of that, there's more circumstances in which software that is maybe not even intended for this purpose could have all sorts of potential vulnerabilities of that nature, in which shell is very powerful. It's not built with that kind of escaping and sanity checking in mind, or at least it wasn't originally built with that in mind. And that kind of vulnerability becomes very possible unless the developer of the script is really taking that into account when doing that. Let's leave things here for today. I want to dive into some more of those weaknesses and vulnerabilities on Tuesday. There's a lot more. There's a little bit more alphabet soup to get through as well.